And welcome back. As we continue our cosmic journey, let's go ahead and talk about now the ocean tides and the moon. So, starting off with ocean tides, what does this have to do with our relationship between the Earth and the moon? Well, anyone living near the sea is familiar with the twice daily rising and falling of the tides. Now, early in history, it was clear that the tides must be related to the moon in some way because the daily delay in the high tide is the same as the daily delay in the moon's rising. So a satisfactory explanation of the tides, however, had to wait until the theory of gravity was developed, supplied by none other than Isaac Newton. So let's look at the pull of the moon on the Earth, because remember, the moon also has a significant mass. Now, the moon exerts gravitational forces on the Earth. The Earth, of course, is larger, so we, of course, have more influence on the moon. And the thing to remember, though, is that these forces between the Earth and moon differ slightly from one another, because not all parts are equally distant from the moon, nor are they the same in all directions. If we look at this diagram here, you can see how some of these forces are pulling at different angles in relation to one another. Now, Earth is not rigid. It might be, of course, a big block of rock, but it is not completely rigid. So the differences among the forces of the moon's attraction on different parts of the Earth, which we refer to as differential forces, causes the Earth to distort slightly. So the side of the Earth nearest to the moon is attracted toward the moon more strongly than is the center of the Earth, which is in turn attracted more strongly than it is to the side opposite the moon. Thus, the differential forces tend to stretch Earth slightly into an oblate spheroid with its long diameter pointed toward the moon. So when we start talking about differential forces, what does this actually mean for our discussion around tides? Well, if the Earth were made out of water instead of rock, it would distort until the moon's differential forces over different parts of its surface came into balance with Earth's own different gravitational forces. Earth would actually distort from a sphere by ranging amounts up to nearly 1 meter. Measurements of the actual deformation of Earth show that the Earth does distort, but only about 1/3 as much as water would because of the greater rigidity of Earth's interior. Remember, our interior, it's primarily comprised of iron at the core. Now, because the tau distortion of the solid Earth amounts to only about 20 centimeters, Earth does not distort enough to balance the moon's differential forces with its own gravity. Objects at Earth's surface experience tiny horizontal tugs. Now, these forces are too insignificant really to affect solid objects, but they do affect the waters in the oceans. And that gets us into this conversation around the tides, which we were trying to get to. So, the tide racing forces that the moon exerts, acting over several hours, produce motions of the water that result in measurable tidal bulges in the ocean. Now, water on one side of the Earth facing the moon flows toward it, with the greatest depths roughly at the point below the moon. On the side of the Earth opposite the moon, water also flows to produce a tidal bulge. And so you can notice here in this image how if the moon is directly across here, so if we follow this across to the moon, you can see we have a tidal bulge here, which of course makes sense because that's the direction it's pulling, but on the exact opposite side of the Earth, we'll have an equal tidal bulge out. Now, tidal bulges in the ocean do not result from the moon compressing or expanding the water, nor from lifting the water away from the Earth. That's a misconception. Instead, what is actually happening is the result from a flow of water over the Earth's surface toward these two regions, below and opposite the moon, causing the water to pile up to greater depths at those places. So, again, this is not a compression of water, it's not an expansion of water, because we're not changing the amount of water that's there, and we're not physically lifting water up and away from the Earth. Instead, it's just how that water is flowing during that time. Now, that leads to things that anyone who's lived in the ocean is probably familiar with: high tide and low tide. Now, during a day, an observer would be carried through two tidal bulges, one on each side of the Earth, and so would experience two high tides and two low tides. This image here shows a side-by-side comparison of the high and low tides. And you can see, in the high tide, we have much more water in that zone versus when it's low tide, because again, referring to those tidal bulges of how the water is flowing. But there's also another force that we have to consider, which is that of solar tides. Because just as the moon is pulling on the Earth, the sun, of course, has its own gravitational pull. Now, the sun also can produce tides on Earth, although because of its distance to Earth, it's less than half as effective as the moon. Now, the tides we actually experience are a combination of the effect of the moon and the sun. Now, when the sun and moon are lined up at either the new moon or the full moon phase, the tides produced reinforce each other, and so produce tides that are greater than normal to form what we refer to as spring tides, which you can see here in diagram A. Now, when the moon is at either the first quarter or the last quarter, the tides produced by the sun partially cancel out the tides of the moon, making them much lower than usual to form what we refer to as neap tides. So when you have this perpendicular effect, where they're at this right angle to one another, we're going to get a neap tide. But when they are along the same plane here, which is again at the new or full moon, we're going to get a spring tide. So why are some of these tides different? Why don't they always measure to be the same, for example? Well, if the Earth rotated very slowly and was surrounded by very deep oceans, our tides would look the same regardless of location. But one thing to keep in mind is that that's not the case, because the presence of land masses kind of stop the flow of water. And the friction in the oceans and between the oceans and the ocean floors, rotation of the Earth, the wind, the variable depth of the ocean, and all other factors really kind of complicate this picture of, if let's say if our tides could move, let's say the high tide and low tide, let's say a 10-meter shift each time, then that would be great if things were all consistent. But because of the way our planet is set up, we don't have that same consistency. So that's why some locations might have different tides. This is why in our real world, some places have very small tides, while at other places, huge tides can actually become tourist attractions because of the huge difference between the high and low tide.